Hey guys, welcome back to another episode of Simuleos. Today is going to be a pretty good day. I'm pretty excited. We're going to see how far we get with this. So here's the truth. I don't understand really what we're going to be doing. And the truth is, I don't think very many people do, but I am looking forward to trying it out anyway. So this is going to be an attempt to visualize fourth dimensional stuff. So let's go ahead and just, what am I doing? Let's just go ahead and go over here real quick. And let me just Google something. Okay, so if we go to fourth dimensional, let's say rotations. There we go. Fourth dimensional rotations. We go to rotations, four dimensional Euclidean space. We have something that's going like this, okay? This boggles my mind. And I'm sure it boggles a lot of other people's mind. This is a representation of a 4D object. Now, how it represents a 4D object, we're going to talk about that because it's not exactly trivial. By the way, Tasty Livero, thanks for coming in. And everyone else who might be on the channel at this point, thanks guys for coming in. What we want to do is we want to generate this image. And I want to figure out exactly what goes into it because I keep hearing people talk about the fourth dimension. It happens all the time. And I have no idea. Literally, okay, a bit of an idea now that I've studied it. But I don't know what this means, you know? I can't really explain it. So let's go ahead and let's explain what I currently understand. And then we're going to go from there. Oh, Zernal. Okay, so let's talk about it. Where's my board? Here it is. Okay. So let's do it this way. If I have a line in space, let's just do a line here. I can continually cut the line, something like this. Let me see. Cut. And guess what we have? Is this in 3D modeling context? Kind of. Okay. So if we cut the line, we get a whole bunch of 1D points, right? So these are going to be 1D points, which I'm going to denote in blue at these locations. Okay? So what we've done is we've taken a two-dimensional object and we split it into a whole bunch of, I suppose, zero-dimensional points? I don't really know how to describe that. Anyway, now, because I thought fourth dimension is in 3D modeling just because it's easier to calculate. No, we are actually going to be doing projections from 4D onto 3D. That's what we're going to be doing. I want to understand the fourth dimension. So I'm going to be doing that. That's exactly what I'm going to be doing. We're not going to worry about the OpenGL stuff where for some reason everything's in the fourth dimension. That's 3 dimensions plus time. This is 4 spatial dimensions. And we're going to see what we do from there. Okay, so now if we do a 2D plane, let's do page, new page before. Let's say we have some sort of square, something like this. There we are. And if we... Yes, that's exactly what we want to do. So then we cut along the square, something like this. We get a whole bunch of lines, which will be again in blue, something like this. Okay? So if we take a 2D plane and we cut that guy up, we get lines. Now, page, new page before. If we take a cube, here's one cube. Here is another cube. Okay, that one didn't, yeah, it's fine. Okay? And we cut this guy up. Let's cut it along here, I suppose. Ooh, this is going to be hard to... I guess we have to cut it like this. Something like this. Anyway, you get the idea. If we cut it along here, we get a whole bunch of planes. 1 second. I have trouble drawing planes. Okay, something like this. We get planes. Okay? So we've taken a 3D object into 2D. So in this way, page, new page before, we can take a ND object. Let's say we can take 1D, 2 points, 2D, 2 lines, and 3D, 2 planes. Okay, so what does this mean? Well, this means if we move on to a fourth dimensional object, let's go here, fourth dimensions should move into some 3D object. And my argument is if we use something known as a tesseract, which is a fourth dimensional cube, so to speak, we should be able to see cubes. Okay, so let's see what we're talking about here. Page, new page before. The formula for a square is going to be, let's say, I guess I'll put E on the end here. It's going to be equal to AX plus BY. That was a Y. 1 second. ax plus by. Okay, so this basically means that our square has some sort of, you could call it radius. It's akin to what we do for the circle, which is x squared plus y squared equals r squared, you know? So we do this for the circle, and the this equation is similar for a square, okay? Now for a cube, e is going to be equal to, here, let me just do square, circle, cube, we have e, one second, that was not what I meant to do. E is going to be equal to ax plus by plus cz, okay? Now, this is kind of neat, but we can go further. New page 4. We can do a 4D cube, also known as a tesseract. And the 4D cube, also known as a tesseract, has the equation E equals ax plus by, I do it every time, plus cz plus dw is what I'm going to say for that dimension. But in essence, it could be any character. We could use w, we could use h, doesn't matter there. Okay, so now what do we need to do from there? So how are we going to visualize something that we cannot visualize? How are we going to see something in the fourth dimension? Well, we do this with something known as shadows. So let's talk about it. In 3D space, in order to go from a cube to a plane, this is what we do. We say, well, we have E equals ax plus by plus cz, and then we just ignore the z dimension. We say, okay, we're going to take z equals 0, or z equals 1, or z equals 2, or something like this. So this is now a constant, and we then say E minus cz is going to be equal to ax plus by. And in this way we can have a plane that goes from, well, you know, whatever z value we want. We can just move along that z value and continually slice up our cube again and again and again, going all the way up our cube to create some sort of series of planes. How do we do this in fourth dimensions? Well, we do the same thing. New page before. We have ax plus by plus cz, right? It's going to be equal to E minus dw, okay? Now, if we give the w some sort of constant, we'll say it varies from, let's say, -1 to 1. Then what we do is we can basically create a cube, right? So we'll have a single cube, which represents d equal 1 value. Hey, happy little rat. We have a single cube, which represents 1 value here. And then we have, I accidentally drew this skewed, my bad, another cube, somewhat outside of this one, that represents another. Oh my gosh, this is awful. I don't know. I'm sorry, guys. I don't know what I just did. That was not what I meant to draw. But the point is, we have a cube that represents when d is equal to -1, and we have another cube that represents when d is equal to 1. And what I want to do today is visualize this right here. Visualize what is known, or what is classically seen, as a tesseract. But we have to go further, because just visualizing the tesseract does not give you a full representation of what the fourth dimension is and why it's so weird. So let's go to new page before, and let's talk about rotations. Okay, so if you want to see a 3D object in full, what do? You take the 3D cube, you stick a line through it, something like this. Yeah, I'm sorry, I screwed that one up. You stick a line through it and you rotate along this line. And by rotating along this line, you will eventually see all the vertices of the cube. You go like this. Take Slivero, in n dimensions this gets super complicated. I'm not gonna lie, I would love to do an n-dimensional thing, but I simply cannot at this point, because I don't know how to. So let's start with 4 dimensions, where it's, you know, easy. And then we go on to multi-dimensions from there. I've been thinking about it, and If you guys like this four-dimensional stuff, yeah, sure, we can definitely go further. But if you guys don't like it that much, we'll go ahead and stop and move on to the next thing. Okay, so by rotating this guy along some direction here, we have, well, the ability to see everything here. But let's talk about rotation in a little bit more detail. Here's our rotation axis, and if we rotate along here, we have essentially a single plane that is, in a sense, not moving. You know, the X and Y coordinates are moving, but the planes along Z, they're not. They're all kind of stationary, right? So, in four dimensions, you can imagine we have two of these planes. We have an XY plane, or additionally a ZW plane. So if you just rotate singly along XY or ZW, we'll get about what we expect, some sort of 4D object, as we see from its shadow, rotating in some direction. However, because this is fourth dimensions, we can do something known as double rotations. We rotate in both XY and ZW at the same time. This is two different rotational axes, and if they're rotating at the same exact angle, we get this. Now, why we get this, I am not exactly sure. This is something I need to do some studying into. So that's basically what I want to do. I want to explain what I currently know of the fourth dimensional rotations, and then I want to just do some rotations and see if we can generate this. And if we can, I feel confident. Sorry about that. I feel confident that maybe we're okay. But let me describe something else here real quick. So there's something known as flatland. Flatland. Okay? So in flatland, we have, let's say, a person. Okay? This person knows up, down, left, right. These are the axes he knows. Now obviously we, living in a three-dimensional world, know at least one more dimension, and that dimension is the world coming out of the plane right here. But this guy doesn't know that. He doesn't know it at all. So because he doesn't know this, if we as three-dimensional objects try to interact with this guy as a two-dimensional object, he will not be able to fully grasp how we're interacting with him. For example, if we, let's say, put our hand down here, if we put our hand on this particular scene, we'll see something that looks like this, right? So here's our four fingers, here's our thumb, but like, you know, our hand is a 3D object. Wow, that was a very bad hand. Let's pretend it's a turkey. Yeah. Anyway, point is, if we put anything into this world, this two-dimensional flatland, no matter what we do, it's going to be projected onto two dimensions. And this is kind of the way that four dimensions is seen to us. No matter what we do, it's always going to have to be projected, which means it's, in a sense, impossible to visualize, and unfortunately, we have to be okay with that. You know, I'd love for a way to better visualize fourth dimensions, but this is as good as I can get. So what we're going to have to do is just learn to live with the fact that we're only going to be able to see the fourth dimension. We're only going to be able to see the fourth dimension in projections. Thanks for the image, Tasty Livero. Okay. So this is the whole idea. There's nothing more to it. I just want to be able to better understand 4D objects. And then once we have that, we can move on to more complicated 4D objects. Anything we want to do, that's fine. We can do whatever we want. But right now I want to get the basics down, and then I want to go from there. One last thing that's super interesting about this. New page before. Okay, we can start with a zero-dimensional object, and the zero-dimensional object would be a point. Let's say, yeah, a point. So 2 to the 0 is equal to 1 point. Now, we can then move to a one-dimensional object, which is a line. 2 to the 1 equals 2 points. Now, if we do 2 to the 2, this is going to equal to 4 points, and if we draw all these 4 points connected, we get two-dimensional space. So if we do 2 to the 3, we get 8 points, which of course is an 8-dimensional object, or I'm sorry, 3-dimensional object. And finally, if we do 2 to the 4, we get 16. What does this mean? Well, it means imagine having a second cube over here. 1, 2, 3, 4, 1, 2, 3, 4. All these guys are connected, and then all of these points are connected too. So this one's connected there, this one's connected there, this one's connected there, 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 and there. Okay, something like this. So it's a cube connected to a cube. And obviously if we keep increasing the dimensions here, 2 to the 5, we get 32, 2 to the 6. We get 64. And in this way we can kind of sort of model all of the dimensions by the number of points that they're going to have in order to fully represent the space. And this is kind of a way to do it. So I'm just kind of pointing that out in case you're interested. There is some relation here, although at this point in time, I'm still kind of fuzzy on how this all works. So, again, guys, I guess you could say I'm a bad physicist for not really understanding the fourth dimension up to this point, but we'll see how far we get. So, unfortunately for this, guys, we're going to have to be doing basically just visualization scripts for the most part. So we're going to see how far we get. And hopefully, we can get far enough, you know? The point is, every time I look up videos on the fourth dimension and stuff, basically people just say, oh wow, this is so interesting. Oh, it blows my mind, and that's fine. But I don't understand it when people just say, oh, it's crazy, it blows my mind. I want a video out that just explains how we understand the fourth dimension without trying to make it fancy, without trying to make it, how do I put this? Like fantastical, you know? So many people are just like, oh, this science is so cool. Obviously it's cool, you know? You don't have to tell me it's cool. I understand that. What I want to know is how it works, you know? This is kind of the thing that I don't see very often in all these videos. And that's kind of what I wanted my video to be about. Just kind of a way to intuitively understand fourth dimension. And I figure if we code it up ourselves, we should be able to get to that point. Anyway, guys, I'm going to get a quick sip of water, then we'll go ahead and get started. It's going to be a little bit messy because we're going to be using Blender for the visualization, but it should be okay. We'll see how far we get. That means that the simulation itself is going to have to be in Python, which is okay, but, you know, we'll see how far we get. One last thing I want to point out. Oh, shoot, I forgot what I was going to point out. I'll remember later. Sorry about that, guys. Keep you in suspense. CD Projekt, Simuleos, and Visualization. I'm going to do an ls here, and let me go ahead and make a new directory. And this is going to be fourth dimension. Hey, Slayer Darth. Oh, that was meant to be an underscore. Okay, so let's go ahead and CD into fourth. Now let's go over here. CD Projekt, Simuleos, and Visualization. Now we're going to do fourth dimension over here. Oh, yeah, that's it. Okay, so, are you a real physicist? It's just that you don't have a LinkedIn profile. Oh, no, I don't have a LinkedIn profile. I suppose I could create one, but I've never had an incentive to. LinkedIn is typically for people who, let me see. I do have a Google Scholar, but I don't have a LinkedIn. LinkedIn is typically for, like, industry people. I don't think I've ever really seen people get a job from LinkedIn in academia, but maybe I should create one before going to a first postdoc. The thing is, I think I already have my first postdoc kind of sort of lined up. I know where I want to go, and I'm going to be talking to different individuals at that institution pretty soon. And hopefully, after speaking to these people, they'll say I'm okay to work there as a postdoc. The thing is, I have some ideas of where I want to, of what I want to do with basically my life right now. But unfortunately, I really need a postdoc. I really, really, really need to better understand some stuff. And so I want to do a postdoc somewhere where I can just learn from the best. And then after learning from the best, I can go out and I can go to academia, I can go to industry, I can go to national labs, I can go to wherever I want. But point is, I still need to learn from the best. So I need a postdoc there. Also, it is getting hot in here. That's probably my fault for wearing long pajama pants today, which I do wear all the time. Okay, so let's go ahead and keep going from here. Let's do an ls back directory. And let's see, we have determinate eigentest evanescent fourth dimension Monte Carlo. What was the very last thing we did? We did a visualization of determinate eigentest demon? Wait a minute. Did we do... One second, I have to think here. What was the very last visualization we did in 3D? Color quantization. Okay. So now let me do an ls. One second. Let's go to color quantization. And let's see, we should have a color quantization.py. Sure do. So let's cp color quantization dot pi over here. Okay, postdoc in machine learning. You should do your postdoc with Gustorn. No, I don't intend to do machine learning for a postdoc. I like machine learning, don't get me wrong, but it's not something I want to actively study. It's a tool that I will use when needed to do basically optimizations of sorts. For me, machine learning, although it is incredibly cool, is not nearly as cool to me as like different computing architectures, like for example quantum computing and cognitive computing. At this point, I'm getting to the point where I understand quantum computing, but now I need to get better and understand cognitive computing, you know? And basically I want to, what I would love is to have a research unit that is dedicated to basically writing algorithms for different architectures that exist or don't exist. Like that's the whole point of my research unit, just executing algorithms in different I guess architectures and things like that, and maybe working with new architectures and stuff, seeing what the utility is. That's kind of what would be neat for me, but we'll see how far we get, you know? Truth is, as long as I'm doing some sort of research, I'm pretty happy. You know, I like the idea that I'm learning new things all the time. It's pretty cool. Okay, so let me go ahead and now CP, or rather move, color quantization dot pi into fourth dimension dot pi. Okay, so now we're going to do something really stupid. I'm going to modify this, and we're going to work from there. Now, here's the thing. I've been modifying this Python script a lot, and what I should probably do is put it into a library, like what I've been doing for the Cairo stuff, but let me do this one visualization, and we'll go from there. I want to do my postdoc in playing DOS games all day. You see the point? Normal people think machine learning is cool because they don't understand it, and when you get to the next level, it's only a tool. Yeah, well, that's true, right? I mean, that's how it is with everything. For example, like this 4D stuff. I spent hours last night trying to figure out how to do a 4D rotation. You want to know what it was? It was just two freaking 2D rotations put together. And I'm just like, come on, guys. Why did no one tell me this? Obviously, you can do two separate 2D rotations at the same time because we have two free planes after doing a single 1D rotation or a single rotation along one axis. And I was like, of course. This is obvious. Why did I not think of this? Always happens. Always freaking happens. Let's do fourth dimension dot pi. And now we have to add in an additional line over here. Let's go down here, change it to fourth dimension dot pi. Okay, I've installed DOSBox, but I've never played any DOS games before. So I don't actually know very many DOS games at all. Like, I don't know which games we're talking about here. I assume these are like super old school Windows games, right? I don't play Windows games very often, so I apologize for that. So what are we going to do here? We're going to visualize fourth dimension. Whoa! Okay, this code can be run by blender-p, mp, yep, name the boxes so that they'll appear appropriate for cage set, dd there. Okay, now, nobody thinks to state the obvious. Yeah, that is true, right? I mean, happens all the time where, hey Kark, it's been forever, man, how have you been? As a form of boxing one's, wait, what? It's a form of boxing one's thoughts. Oh, fair enough, yeah. So, I mean, I think you're right, happy little rat. It ends up being that for me, when I'm describing something, I always want to hit the stuff that took me forever to understand, you know? So I'm going to go through and I'm going to be like, oh, this is super difficult, I don't know how to do this, but all the stuff that other people have already said, you know? So all the stuff I've read in papers, all the stuff that people have told me via classes, all this stuff I assume is a given to everyone else. So I don't just go and say, oh, this is how it's done. Even though that stuff may have taken them hours and hours and hours to understand, they can always provide it in an intuitive fashion. And because they can provide it in an intuitive fashion, it just, it makes everything seem easy. And that's the problem. Let's see, does anyone know where I can find DOS sharewares? No, I don't. Sorry about that, Slayer Darth. Good luck. That's why you have rubber ducks in industry. Yeah, that's also, yep, that's why you, yep. If you don't get it, just tell the duck and you get it. Yeah, but the issue with that is, like, seriously, I have been spending, and you guys are going to laugh when you hear this, well, maybe not, but I spent the entire last week just trying to get a freaking in-place transposition on my CUDA card for a large object. It's been less that last time I showed up. It's been pretty much fine. I started playing with C++ at school, but my teacher knowledge is pretty obsolete in my opinion. iostream.h and dev.cpp. I don't actually even know what these are. WBGIM? I don't even know what they are, so maybe they're great. For me, Cork, I've just been doing work. And working on little things here and there. Hopefully, I don't know. We'll see. So I was actually kind of... The last simulation we did was one of viral videos and stuff like that, which I thought was super cool. However, unfortunately, it did not... it wasn't so popular here on Twitch, and I'm kind of curious as to why. So I'm going to see what happens. I think maybe it was just an issue because I wasn't able to stream every day or something like that. He just learns to theory and does everything. That's basically my life, right? I use G++. Yeah, everyone uses G++. G++ is super common. Well, not everybody. People use Clang, which is super cool. I mean, I'm currently working in a theoretical physics lab, right? Oh, by the way, guys, I have a stack like this big. It's a huge stack filled with papers that are just like, they're filled with ideas of things that we can do. And I just, oh gosh, there's so many ideas. So many ideas. And I just want to do everything, you know? Because the more I do, the more I learn, the better I am, and that's kind of the way I see it, you know? There's no reason to be bored when you have so much stuff that you could be doing at any given moment in time that is just for fun, just to improve yourself, you know? But this is, of course, my opinion. Everyone else has their own opinion, yada yada. Okay, so what do we need here? Well, to do the visualization, we're going to need a few things, and let's go to make sure... I think I said Clang. Did I not say Clang? If I said Cling, I meant Clang. Okay, so let's go up here. What do we have? So we're going to need a couple different functions. We're definitely going to need a function to place all of the new spheres. However, in this case, we don't need the functions to parse the data because at this point, all of these simulations will be done in Python. This is okay, even though Python is slow, we should be perfectly okay doing this. If your stack topples over, it will be a Stack Overflow. Too bad I'm good enough to implement them. Yeah. At least you're not running out of ideas. Not good enough. Oh, too bad no, but that's the thing, right? So I've got a friend. Me and him, and he will remain unnamed for a number of reasons, but me and him, oh, I'll name him. His name will be, Joseph. It's not his actual name, I just made it up. But me and Joseph, we're currently going through a book right now on, finite element methods. Now, he doesn't know that much about C++, and I know a good bit more than him, though I'm not going to claim I know a lot about C++. Anyway, here we are, we're working with this language, and the book is written in Fortran, obviously, because Fortran is the #1 language for scientists, and look, guys, I know what you're going to say, Fortran, oh, I hate Fortran, but man, the more I'm reading about it again and again, I'm remembering why I love Fortran. It is super nice. Gosh. Anyway, point is, for matrix stuff, like, gosh, it makes matrix stuff easy. All that matrix stuff that's easy in, for example, MATLAB, came from Fortran. I love Fortran. It's great. Let's see. First two GTAs were the only good GTAs. I thought G++ was a compiler. Yeah, it is a compiler. Let me see. Okay. I could do Fortran Friday again. I look in to my prof neural network code done in Fortran. Stopped after 30 minutes. Oh, come on. Fortran is super nice. It's fast, first of all. It is as fast as C++ and easier to write. So this means that if you're writing Fortran code, you're doing a lot of calculations, and these calculations are going to take a day. Unless you're doing GPU computing, if you're working on the CPU, I would still recommend Fortran to look into. You know, it's one of those languages that just it keeps coming back. You know, it's good. I see why there is hate in the computer science community for Fortran, because there are so many different techniques to writing it, and there's so many ways that you can make Fortran look ugly. But it can look like any other language, you know? It's just a lot of people make it look ugly because they do like all caps for their names and stuff like that. But I don't know, I like Fortran, you know? It's not a language I use every day, but I genuinely like it. Okay, anyway, I've been rambling for way too long. Let's go ahead and let's see what we need. So we're not going to need the parse data functions or the parse octree data. And because this is going to be a specific function written for the fourth dimension stuff, let's just go ahead and remove these for now, and then we'll kind of add them in as they're needed. So because we have these somewhere else, I'm just going to remove these guys, and we're just going to have the basics of what we're going to need. So what do we have here? I played around with FEM simulations, then I added things. At one point, my ball of smoke fell to the ground and bounced off. That's about right. I mean, this is kind of the thing I like about simulations. It's one of those things that you can get an intuitive feel for what the world is doing, you know? And I like it, you know? Because you can spend time just learning about things, and it's exclusively a learning environment. A description of WBGIM library from the CS department in Colorado University. The following functions are mostly from the original Borland graphics interface for DOS programs. The BGI graphics functions may also be used with Windows programs created by the Borland 5.0 compiler, the free new C++ compiler, and possibly other compilers. Yeah, so G++ would be the free new compiler they're talking about. Probably the best unexpected behavior I've ever encountered. You know, that's how it is. Simulations happen, and I love simulations because, like, I don't know, I like them. They're super fun. Anyway, let's keep going. Create new material. We're going to need this one. New sphere. We're going to need that one. New sphere Monte Carlo. What is the difference between new sphere and new sphere Monte Carlo? I think the difference is X, Y, Z, R, G, B, I, D. What is the difference? One second, I got to think here. Def new sphere. Return temp sphere. Is there a difference? I have to think. Segments 8. OB, object. OB.name equals string ID. Yep, that's fair enough. Let me see, what do we have here? Me equals objects.data, color, RGB. Is there a difference between these two functions? I am not seeing a difference. ob.name, ob.color, material appends mat. The only difference I see is the segments 8 versus segments 32. So I'm going to remove this function. This is gonna be like the least entertaining stream ever, because like I'm just kind of looking at old code and seeing what happens. But you know, I don't know. So place duplicates. By the way, for example, in Blender, but I think this is true for OpenGL too. Happy Little Rat, feel free to correct me if I'm wrong. The optimal way in order to basically put a whole bunch of points down is to place down these points as duplicates, and that's super useful. Slayer Darth, what is your idea? Place spheres, what do we have here? Let's see, determine the final velocities for coloring. Move spheres, okay, fair enough. And let me see. Okay, so then we're gonna move spheres, array, numpart, okay. Maybe you could have one of your streams about trying to code a text-based adventure game in C++. I actually did have a stream about that a while back. We used, sorry about that, but it was in Python, I think. I was doing, what is it? It is the terminal-based visualization. It is, what is it called? What is the terminal-based guy called? Curses, and curses, that's what I was using. So I was using curses to do the visualization, and after doing curses to do the visualization, I mean, it was kind of neat. I really liked it, and at some point, I really want to go back and just finish up my terminal-based, let me see, where are we? So if we go to Simuleos, and we go to Info, we scroll down to GitHub, click on this guy here, and we go to Laos. Should be able to, I'm not sure exactly where it is, but I know it's going to be in here. Terminal Velociraptor. Yeah, so basically, we created a terminal-based, how do I put this? A terminal-based academia-themed card game that was played, you know, obviously in the terminal. So you open up your terminal, you play with, you know, basically the computer at this point. We never got it quite finished, and what I might do, guys, if you guys want, I might take a day off. And I might just spend time working on this game again, just to kind of finish it up, you know, just to say, hey, we're done with it. So I don't know why it was called Terminal Velociraptor. We didn't really have a good name for it. They wanted it to be the code name M-Oist, which is like massively multiplayer Oist. But it never really became multiplayer, let alone massively multiplayer. So they just wanted to call it Moist. and then we go from there. Anyway, point is, it was actually quite fun. The idea was you have to get like the maximum impact factor or something like this, and in order to get the maximum impact factor, you have to like continually publish, and you can like kind of be mean to other people or the other players. It was kind of like a Magic the Gathering-esque game, except your mana was basically like the postdocs and students and graduate students in your lab, you know, and that was kind of the idea. It was actually kind of fun. Okay. Oh, and every time you publish, like, basically there is a random chance, like, you just roll die every time you publish, and you keep rolling die until you get into a journal. So, like, you have, like, a 10% chance of getting into Nature, like, a 5% chance of getting into this journal, a 15% chance of getting into this journal, and you just keep rolling until you get into an actual journal. And then when you get into the journal, it just, you publish there, your impact factor goes up, yada yada. Okay, so what are we going to do? Move theorist is also important. Move lines should be good. The function assumes that balls have already been moved for the first time step. I've been looking at least for at the last of your commits since I can chew a bit of C++ now. And from my understanding, Cairo is a simple yet useful graphics library. Yes, that's basically what it is. It's a two-dimensional graphics library that I use for most of the visualizations. I got Zork installed now. Good for you. Okay, so create cage. That seems good to me. Cage set seems good. We might need that. Let's see, remove object, define scene, all this is necessary. What do we have? Keep going. Add lines. This is probably necessary with a connect to me. Yep, that's fair. I died to a troll. I'm sorry. Okay, so what do we have here? Create connect to me, that should also be good. Now let me see, what are we doing here for create connect to me? I think, yeah, this should be okay. And now let me see, render movie, hide interior. So these are hide interior. What do I need hide interior for? Let me see. There we are, Monte Carlo. Okay, so we can probably remove the Monte Carlo guy. Yeah, let's remove the Monte Carlo guy. And then we'll kind of go from there. So Monte Carlo is currently being removed. In interior, can probably also be removed. In exterior, can be removed. Create NC spheres. Again, probably don't need this one. Visualize Octree, don't need that one. Good. So I think we have all the functions we're going to need. Now let me go up here real quick. Dwarf Fortress is a real text-based adventure game. Maybe. So let me see. Hide interior. What is this guy? Yes, hiding cube until a particular time. Don't need this guy either. Okay, so now we have all the functions we need. I'm just going to go ahead and write this. And now let's go ahead and define our first function here. So we're going to say function. Oh my gosh. For. What do I want to do first? I guess I just want to do visualizing a tesseract. So let's say creating a tesseract with connected points. Okay, so what are we going to do then? We're going to do define tesseract. Okay, 1 second. So I suppose we don't need to read anything in. Maybe we need to read in scene. Yeah, maybe we have to read in scene. This is going to be a little bit weird because I kind of forgot how to code in Blender. So we'll see what happens. Okay, so we have to define the tesseract. Okay, so what do we need to do? Well, first, we need to find the location. 1 second. Find a location of all the points. Okay, so what are we going to do? Well, basically, in order to solve for this guy, all we need to do is solve for that equation that I put up before, where ax plus by plus c z is going to be equal to e minus wd. That's what we need to solve for. Now the question is, how do we solve for this? Well, what we can do is we can start with a unit cube. So x, y, and z are all defined in such a way. And then what we can do is, after defining the unit cube, we then basically modulate the w. So here, let me define this in another way. So new page before. We start with the unit cube. So we have all of our x, y, and z's defined. So again, it's just going to be something like this. 1, 2, 3, 4, 5, 6, 7, 8. And then we say this is going to be, gosh, that was awful. X equals 1, y equals 1, z equals 1. And then what we do is we take the w dimension and we go from -1 to 0. I'm sorry, w to 1. That's what we want to do. So we want to kind of shift the w dimension. And what this should do is it should create a steadily increasing cube. And then what we want to do is basically, how do I put this? What we want to do is basically show the visualization, show the increasing nature of this cube. And then after showing that, I then want to basically, well, go from there. I want to just kind of show the typical tesseract, which would be connecting all of the points x1, y1, z1 to x whatever it is, y whatever it is, z whatever it is, when we have w equal to 1 instead of -1. Is it raining outside? I'm hearing, yeah, I think it's raining outside. It's definitely raining outside. W is the fourth dimension. I don't know why people typically use W, but people do, I think. In fact, there's even an anime called Dimension W. It's awful. Don't watch it. Okay. Finds the location of all the points. My roommate was watching it, and like the intro was awful. It was just like it showed X's, and it basically showed like they were like scientists have found 3 spatial dimensions, 1, 2, 3, and so they draw X dimension, Y dimension, and Z dimension, and then they showed the W dimension, which they just draw in -X, and I'm like, dude. I think everyone has looked behind them before. I don't think you have to draw the W dimension in that way, and if you did, you could definitely draw it in a way that makes it so at least all the axes look like they could be perpendicular in 4-dimensional space. Don't just draw a line backwards. I kind of just give it a lot of crap for that. Okay, so let's go ahead and determine the locations of the unit cube. So let's start by setting locations for unit cube. Okay, so let me think here. If we're gonna set X, Y, you know why the W, fourth letter from the last in the alphabet? Yeah, maybe. That's probably it. Yeah, that's probably it. So setting locations for the unit cube. What are we gonna do then? Well, we need a vector of 8 points. However, in the end, we're probably gonna need 16 points. Or 2 vectors of 8 points. I suppose 2 vectors of 8 points would be better. So let's go ahead and do that. So we're going to go here and we're going to say, oh gosh, I can't remember how to do Python. So we're going to say unit cube here. And then we're going to basically append the data to it. I guess, oh, how do I do this? Unit cube, how do I automatically set this to be 8 in size? How about we say unit cube equals, and I guess we're going to say I for I in range 0 to 8. And this should be 7, I think. Let me just go over here real quick. Let me see. We don't want to render the movie. Scene.update. We don't want to do any of this. But that's okay. So let's go here. Let's go here and let's run Blender -P. I suppose -B. Oh no, it's gonna be 1 second. Where am I? Fourth dimension .py, and then that should be it. This will pull up Blender, but it seems to run, so we should be okay. So we want to do -B-P. No, it didn't run. Dang it. This is me not remembering Python at all. Let's go up here. Let's remove these guys. Blender -B-P. Okay, 1 second. Scientists aren't that great at naming things. Scientists are pretty great at naming things. Wait. Scientists aren't that great at naming things. Scientists are pretty great at naming things depending on the view. Spaghettification intensifies. Yeah, fair enough. So let's go ahead and remove the parse data. Parse arctree data. Let's go over here and let's do Blender -B-P. Num2 is not defined. Of course it's not, because screw the rules. Num is not defined. Oh, I guess we'll just define num. So we'll say num equals 10. I don't know. Scene update. Let's run this and just make sure it runs. Okay, that one runs. Runs. Okay, good. So we have the unit cube. Now let's go ahead and give these guys a location. Now let me think here. The unit cube actually has to have an X, Y, and Z location, right? So each individual point in here must have an X, Y, and Z location. So I suppose the best way to do this is to give each of them. Let me see. We could. Let me go up here and let's create a class real quick. And let's define a class. So we're going to say class. And we're going to call the class point. And in this class, we're going to say x. Let me see. How do I do this in Python? X equals 0. Y equals 0. Z equals 0. And we're going to do def init. 1 second. I think we read in self. And then we want to read in x, y, and z. And I guess what I'll do is the following. Leonard Susskind is great. Recently started watching his lectures. Really seems cool. Yeah, I've heard of the guy. I don't remember what he does though, for some reason. So now we're going to say, let's go up here and let's just say Rx, Ry, and Rz. And now we're going to go here and we're going to say x is going to be equal to Rx. Oh my gosh. Y is going to be equal to Ry, and Z is going to be equal to Rz. I think, unless I'm an idiot. Yes, okay, so this one seems to run with that. So let's go down here. And now we're going to say point of, let me see. I should learn Dwarf Fortress. I've heard very good things about Dwarf Fortress. So let's say 0, 0, 0 for I in range 0 to 8. Blender. Okay, so it seems to run okay. So now let's go ahead and define all these guys' location. So what are we going to do for these locations? Basically, we have to create the unit cube. The unit cube is going to be, let's see, 8 different points. And it's going to be from theoretical physics at Stanford University. Oh, of course. Yes, that's him. I couldn't remember if he's a CS guy or a physics guy. Sorry about that. Sometimes I have trouble remembering things. We're going to get nowhere today because I totally forgot all my Python. But that's okay. You know, some days are like that. Okay, so unit cube. What are we going to do then? Well, basically now we have to plot each of these points. So we define the tesseract. Yeah. Okay, so now we have another question. How do we solve this equation? This is not something I considered. How do we solve the equation as it increases in size? So let's think about that in a second after defining the cube. So let's do 4. Let's say I in range, and we're gonna say 0 to oh, I guess it's just 0 to 1. And this should include 1, I think. Probably. For J in range. Oh my gosh, I can't do this. J in range 0 to 1. And then for K in range 0 to 1. Okay, so now we have to give these guys appropriate locations. We're going to say unit cube of, I suppose it's going to be, wait a minute, I have to think here. Screw it, count equals 0. Let's go here. Count plus equals 1. There we go. So we have a count. So we're going to say is going to be equal to point of, and I suppose we just do I, J, K. And that should be it. So let's go down here and let's do a quick print of count. Just to make sure we did this correctly. No semicolon needed. We're going to go down here. We're going to define tesseract. Okay. And we need to read in scene, but for now, let's just not read in anything. Okay. Define tesseract. Let's go over here. Let's do blender-p. 1. Okay. Let's change this to a 2. 1 second. 8. Okay, good. So now we have all the things defined. Now, what are these values going to be going from? They are going to be going from 0 to 1, right? But we want them probably between -0.5 and 0.5. So instead, what we need to do is we need to define the x, y, and z location. So this is what we're going to do. We're going to say x location. It's going to be equal to, and I think we can do it this way, though I'm not sure, double of I. Let's just do x location, y location, z location. Oh, it's not gonna be double, is it? Oh, let's see what happens. Of j, and now we're gonna go down here. We're gonna say z location is equal to z location is gonna be equal to double of k. Oh, this is gonna break. Yeah, double's not defined. It's gonna be float or something like this. Double's not defined. Okay, so I think it liked float. 1 second, let's go to float. Okay, good. That seemed to work. So now we're gonna say float of I minus 0.5. And that should do it. Minus 0.5. And let's just do a dot here. Then we're gonna say x position, y position, and z position. Okay, so this should be our unit cube. Now, next question. What do we do next? We have the unit cube defined. How exactly do we change that w value? Okay, so let's think here real quick. The w value, as it goes from 0 to 1, let's go here, right? And let's go over here. So we have this guy, and we said it's a unit cube, and as we go from 0 to 1, things change a little bit, right? So what does a unit cube look like? The unit cube looks like this. It has an equation that's equal to, 1 second, ax. So we're just going to say x plus y plus z is equal to 1. That's what it has, okay? So this means basically the length of all the sides are equal to 1. Okay? So now what we can do is we can shift the length of all of these guys. And actually, let's make this go from negative 0.5 to positive 0.5 instead of negative 1 to 1. Okay? So this means that we will have values of this 1 going from 0.5 to 1.5. Okay? How is your Japanese? Do I need to know the basics before studying in Japan, for example? Okay, so here's the thing. You do if you're studying anywhere in Japan except for OIST. The Okinawa Institute of Science and Technology, where I'm at right now, is completely English speaking. And there are a few other universities, I suppose, that are purely English speaking, but the best of the best Japanese universities, besides OIST, because of course OIST is the best of the best, will be speaking Japanese. So you're definitely going to need to learn Japanese if you want to succeed here in Japan, unless you go to OIST, in which case you're fine. This is not an OIST advertisement, but if you want to come to OIST, feel free to do so. I mean, this isn't like, I don't get anything for recruiting you guys except better students at OIST, you know? Like, and that's all I want. I just want this institution to do well, you know, because I'm here and I really like it. And I want other people to like it too. That said, not everyone likes it. That's fine. You really have to consider a lot of things before coming here, but that's okay. But yeah, in general, you would need to learn at least the basics of Japanese. I know very little, though, unfortunately. In fact, people in chat know more Japanese than I do. For example, Gus Torn, he knows a good bit. Then we have, just came on yesterday. What is their name? Oh gosh, they're probably here in chat right now, and I don't remember their name. There was another person, every time they come in, they just write something in Japanese that I can't read, and I feel really bad for it. And then I think, I should learn Japanese, and then I don't learn Japanese. That's basically it. Yep, that's basically it. Okay, so we should be able to vary this from 0.5 to 1.5, and this should basically give us what we want. Okay, so how are we going to visualize that? Well, let's first get our unit cube down, and then we'll go from there. Learning university level Japanese will take a long time if you want to start on it. Yeah. Okay, so now we have all of the points. Let's go ahead and go through and let's put all these points into the scene and go from there. So now we're going to do visualize. Let's do def visualize fourth. Yeah, why not? Fourth dimension. There we go. Let's do it. Let's go up here. Let's see, what do we have here? I guess usually you define main or something like that. I'm only aiming for everyday use, and it's still taking a while. Yeah, I'm aiming for use. Okay, so we create new material. This should be okay. New sphere there should be okay also. So what do I want to do? I want to basically create a new sphere at each of these locations. That's what I want to do. And I'm going to have an RGB value and ID. Now, let me think. new sphere, and then we want to place duplicates. Maybe that's what I want to do. Put the new sphere down and then place duplicates. And then I want to create a connectomy. The main reason for the failure in Dwarf Fortress is just not bothering. Let's go here, and let's, in define tesseract, define the, I suppose I'll call it radius, but I'm not sure what I actually want to call this guy. So I guess we'll call it, I don't know. What should I call it? I will call it box length. There we go. And so now we're going to go here. We're going to say float of I, which is going to be from 0 to 1. And what do I want to do? So we're going to subtract it by 0.5. And then we're going to multiply this entire factor by box length. Oh, let's just do this. Oh, what was I doing? Times box length. Right there. So let's go ahead and drop there, drop there. And these are commas. They should be periods. Sorry about that, guys. So we're reading box length, and this is no longer the unit cube. It's just going to be cube. Let's go over here. Let's change this to cube. Okay, let's go ahead and write this. Go over here. Let's not make it. Run blender-p. Y location is equal to float j 0.5 times box length. Oh, I forgot a parentheses. Dag nabbit. Blender. Visualize fourth dimension, of course. Now needs a something. Let's go here. So what are we going to do here? I suppose this is where, let me go up here, function to plot all the points and create the connectomy. Okay, so let's go here. What do we have here? Main reason for failure in Dwarf Fortress is just not bothering. It's an upkeep game. You need to keep everything running and not miss anything. Okay, so here's what we're going to say. We're going to say, I guess we're just going to define cube. So we're going to say current cube is going to be equal to, how do I put this? It's going to be equal to define tesseract of box length. Okay, so we have this. And now what do I want to do? I suppose, yeah, I know, he came in, but he doesn't seem to be talking very much anymore. Yeah, hey Gastron, I saw you in chat just a second ago. So I guess we're going to say, how about, yeah, we'll have current cube. We need current cube. Define tesseract of box length. And basically what I want to do then is I want to say for, and let's say I equals 0. Then we'll do, how about we go up here and we define a resolution. Okay, and we're going to say, oh, I'm sorry, what am I doing? This is wrong syntax. For I in range, 0 to resolution. We go down here, we say current cube here, and what I want to do is define, let's go here, define small cube first. So first we're going to define the smallest cube here, which is going to be a cube of 0.5. So we're going to say init cube. It's going to be equal to, what do I want here? I suppose I want, 1 second, I have to think here. It should be define tesseract, 1 second, of 0.5. That's going to be as small as we go. And then basically we go up from there. So we're going to do this, and what do I want? I suppose I want the following. So I'm going to say box length is going to be equal to 0.5 plus, let me think here. So I guess it's going to be 1 divided by resolution. Something like this. And then we're going to multiply this by I. So it's going to be I divided by resolution. And I'm just going to change this to a float just to be safe. Because, there we go. Let's run this one just to make sure it works. Define tesseract is missing 1 additional object. Yes, it is missing the box length, so let's do 0.5. Make sure that one runs. Blender. Exposition is not defined. Oh, that's because I called them location. That's my bad. Let's go to 1, 2, 3, 1, 2, 3, 1, 2, 3, and let's add in location. So let's do I location. Location here. location there. Let's go here. Let's see if this one runs at least. Okay, this one runs. Now we have to do the visualizer for the fourth dimension. Now, I have to think here of how we want to do this. Oh, it always has float division in Python 3. And we are using Python 3. So we should be okay. It's okay, whatever, I just defined it. Good. So now what do I need to do? The next thing I need to do is basically define each of these individual points, give them all unique identifiers, and then go from there. The unique identifiers, I believe, will be strings related to their number in the current cube tesseract. Okay, so we have that, and now what we need to do is create the connectome between all the different points. So what am I going to do then? I suppose... Let me see, how did I do this before? The connectome, let me go up here. The connectome is basically the thing that connects all the lines together, and we're okay. And before we're not okay. It's okay. I think today we're not going to get as far as I was hoping, but we'll see how far we get. So let's go up here to connectome, and we should have... There we are. Here, return connectome. That's fine. Create connectome. You know, one thing I totally forgot to do is down here I need to return. At the end here. Return. Cube. There we go. Go up to connectome again. We should just create connectome. It should be fine. Now what do we have? Add lines. This is what I want. Okay. And then we should have a move lines also, I think. So let's see. What do we have here? For I in connectome. There we go. bpi. Ops curve primitive Bezier curve add context object data splines active id name.bc plus string I 0. Okay, so let me see, what am I doing here? Bezier curve plus string of I 0. They're all plus string of I 0. Let me see. Create where? Oh wait, what was in each I? 1 second. I gotta think here. So every I, let me go down to the create connectome down here. What are we going to say here? Connectome is equal to this, count equals this for jk. So now we're going to say k plus connectome.append count pnum plus 1. Okay, so we had 3 guys here. We had the individual count for each. Okay. And then the 2 characters that it's connecting. So that's what we had. Okay. So now what do I want to do? I suppose we have we have to probably figure out how we're doing this. So I suppose if we plot all the points, let me see. So let's go ahead and put all the points down. And then after putting all the points down, we should then probably put down, let me see, where's first pnum defined? Pnum equals 0. Yep. So then after putting all the points down, we should probably define what their IDs are. Get our simple cube done, figure out what all these points are, and then after figuring what all the points are, we then go from there. So let's go down here to the end. Current cube is equal to this. So now let's go ahead and create all of our new spheres and place duplicates and do all this kind of stuff. So let me go to place dupe. Here we are. And ID, OB, ID. Okay, this should be good. Now let me see, did I use place duplicates anywhere? Not at this point. So I guess we'll create a new sphere. And then after creating a new sphere, we will go from there. Okay, so let's do it. Temp sphere is equal to this. bpi ops mesh primitive UV sphere add. So let's just go ahead and create our new sphere. Go down here, and we will define, 1 second, here. So we're going to define sphere material for copying. Okay. So let's do it. So we're going to say new sphere. 1 second. Wait, what did I just look for? Sphere. Whatever. Where is it? Temp sphere, new sphere. Okay. We need the diameter, the XYZ, RGB, and then the ID. Gotcha. So let's go here and let's go ahead and do it. 1 second. I keep feeling like I need to sneeze, but I don't know if I need to sneeze or not. It's one of those days. Let's go here. Open. There we go. So a new sphere. Diameter, which we're going to put down as 0.1. X, which we'll put down as 0. So R0. 0. RGB, let's make it red. Why not? So let's do R as 1. And now we're going to say the ID is going to be equal to original. There we go. Now what we should be able to do, let me go and see what OBID is. BPy objects. Yep, so this should be a string. So now all we have to do is place duplicates and give them the actual location. So I guess what we'll do is that, exactly. So let's see, what do we have here? Copy, data, copy, string ID. Yep, so this should be okay. So it's just 4 integers and then the OBID. So let's go down to G. And we have the current cube, which we have defined as the tesseract. So every time we do this, let's just go through. And let me think. How do we want to do this in the best way? I suppose the resolution is going to be our number here that we have. And what we need to do is add in individual position keyframes for each of these guys. So what are we going to do then? I suppose, let me think. What did we do before with the move spheres? Here we are, move spheres. Material, keyframe, insert, diffusion color. Yeah, that's not what I need here. Material, bpy data, diffuse colors. Foreign range. Ratio. Difference of the velocity. How did I move these guys before? Current frame is equal to bpy. 1 second. I have to think here. This is going to take some time. I apologize for that, guys. Okay, so let's see. What do we have here? Move spheres, bpy context data frame set frame, offset int frame, numpart minus numpart. Current frame is equal to this. Okay, so this should be okay then. We have all the frames set. Now what we need to do, we have the velocity, ratio, material, 1 second, keyframe insert, data path diffuse color, frame equals frame, index minus 1. Oh, here we are. bpy context scene objects location is equal to this. But what I should probably do, yeah, so I need to add in a keyframe for, yep, each of the materials, I think is what we need to do. So we're going to say material. What is material? So the material that we're looking at here is going to be, yep, that guy there. Okay, so I guess let's do it. We'll initially place the duplicates here, and we'll go from there. So if I equals 0, I equals 0, we're going to place the duplicates. We're going to place duplicates of these guys. We're going to say 4. J in range. How about J in init cube, current cube? 1 second. Current cube is equal to this. So let's say J in range. Actually, let's just go up here and do it this way. So init cube is equal to this, and let's just do it twice. So we're going to say, wait, what? Oh, dagnabbit. Maybe I should just do this on my own. I mean, this should be fine, right? So the Blender code, basically, we have the Python code. Now what we're doing is we are defining each of the individual locations of all the different spheres. That's all we're doing. Then once we get all the locations done, all we have to do is connect all the points together with the Bezier curves. And then after connecting all the points together, we then just have to move everything with the keyframes. That's all we need to do. And then we should be good to go from there. So sorry about that. I guess it's not particularly interesting to watch. Yeah, hopefully tomorrow will be a little bit better, I guess. Let me think. Yeah, I don't think there's any way I can change that. Okay, so let's go through. Yeah, but we're not really using anything here, right? At this point, we have the new sphere command, which literally just creates a new sphere. And then we go from there, you know? So I think it should be okay. Anyway, let's go here. Oh, fair enough. Okay, so let's go here. And let's go and let's define each of these locations. So we're going to do 4. And let's do I in init cube. Then we should be able to do this. So we're going to say place duplicates. And what do we want to place? We want X, Y, and Z, RGB, something like this. So what do we want? We want the OB ID. What is it? Here, there. Okay, so it's, 1 second. X, Y, Z, ID, and then OB ID. So X, Y, and Z are going to be equal to I.X, I.Y, I.Z. OBID is going to be original. And then the I is going to be count. That should be okay. We'll go up here and we'll say count equals 0. We'll go down here and we'll say count plus equals 1. There we go. So now we have all these guys set. And now we have to do it one more time. For I in init cube. Let's go down here, and we're basically going to follow the same lines. Place duplicates of, let's go here to I.X, I.Y, I.Z, original, and count. And we should be able to do count plus plus. Plus equals, oh, what am I doing? Plus equals 1. Hey guys, don't have to see you. I went away for study. To study for tomorrow a bit. I did actually forget to tell James to say hi when he saw you. Hey, okay. Guster and Kark said hey. So let me see, 1 second. We have count plus equals 1. For I equals, yeah, this should be okay. So let's just go ahead and plot these guys. Comment this guy out for now. Here, and go down here. And this should be okay. So let's go ahead and do blender-b-p. For I in init cube, that's fair enough. Blender. Okay, this one seems to run. So now what I want to do is visualize the fourth dimension in here, and hopefully this will work out okay. So let's do here, and we're going to do visualize fourth dimension, and the resolution is going to be, let's say, 10. Not that it really matters here. 1 second, probably because that would be a smarter idea. Let's go here. And of course nothing was defined, that is fair enough. Let's see if we can figure that one out. Since you seem to know it all, Mighty Gustorn, what do you know about, do you know what WebGM is? Yeah, I could definitely do that. I mean, either way we end up doing the same thing, right? So basically I want to place, let me think. So count plus equals 1. So let's see, place duplicates here. Oh, I suppose that's fair enough. Let's do place duplicates twice. And then we'd say place duplicates count, and then count plus 8. And that should do it. Okay, so now the question is why this isn't quite working the way I want it to do. So fourth dimension blender-p, blender.py. Let's go here. So why is it not plotting anything when we do new sphere? It should plot something at the original location. Let's change this to like a 10 or something like this. Let's change this to like, I don't know, like 30. Go to blender-p. Yeah, of course it doesn't exist. Scroll down. Okay, but we do have particle number 30. Oh, we also have particle number original. Wait a minute, maybe I just screwed this up last time. Let's change this to original. Original. Let's go here to, 1 second, let's make sure it's written. Let's do blender-p. Let's see, what do we have here? We have original there. Let's move this cube out of the way. Okay, so we do have a single dot. Okay, now the question is why we don't have the other duplicates. So we have the original guy. He's fine. We have one single dot. Okay, let's see what we have. Shouldn't you count plus init cube? I guess we could do plus length of init cube, and that's fine. Okay. So what are we gonna do then? Define tesseract 0.5. Should be okay. We are returning the cube, so let me just go print init cube. Let's go from there. Let's go here to blender-p. Let me see. OBID, index 8 out of range, size 5. 1 second, let me think. What is the issue? What is it? What's happening here? Screw you, Blender. Okay. That's not what I want. Let me see if we can figure out what this error is. So let me run blender-b-p again, which makes it so it won't run Blender. Now let's see, what do we have? Is W for Windows? Okay, what do we have? Visualization, 4th dimension, 382. Okay, then it's gonna be 374. Then it's gonna be 61. Okay, BPy data objects, and it says index 8 out of range, size 5. Let me see, OBID. Let's go down to place duplicates. Okay, that's the problem. I put them in the reverse order. And let's go to original. And let's go here to original. And let's do blender-p. That one seems to run. Then we have this guy, which I'm not sure exactly what's happening there. Okay, so let's do blender-p. Now we have nothing. It's all broken. Crap. As in... Okay, so then what is happening here? What is all that nonsense? Place duplicates there. We had a single point being plotted before. I have no idea what this is over here. Did I see 4th dimension? No, you did not yet. No, we aren't there yet. We're getting there. We're getting there. Give me some time. We are totally getting there. Okay, so what do we have here? Why is this guy giving me all this nonsense pointer stuff? Let me get a quick sip of water, and then we will kind of go from there, and we'll see how far we get. Okay, A is equal to... So good that Microsoft had to kill it? Okay, under what circumstances would you get this kind of gobbledygook in Python? No idea. None whatsoever. In main point object 0 point, I don't know what to do here. So let's go right. Let's try it one more time, blender-p. Okay, so we're still getting that stupid nonsense. So let's go ahead and just comment these guys out. 1 second. Here again. Right, let's go here and let's run blender-p. 1 second. So now we don't have anything anymore. What happened to the things we had? Let me make sure it's written. Try it again. We totally had a dot there last time. 1 second. Where is the dot? Let me see. I've never seen 4D physics. I mean, 4th dimensional stuff is used a lot in physics. It's kind of a way to, I don't know. It's a way to describe certain physical phenomena. I'm not going to go into that, what exactly that is, but that's okay. They didn't sell license to new DirectX or Borland. To Borland. Anybody cares to explain or correct me things? Oh, okay, I see. Okay, so now we have a bit of a problem in that, for some reason... So maybe we're stopping here. Let's go here. Blender. Okay, so that one seems to run. We don't have anything being drawn, but that's maybe okay. Okay, that's okay. But it's not doing what I want it to do. So let me see. How to kill a good physicist. Mom, Microsoft is good? Oh, good project. Oh. Okay, so what do we have here? New sphere. Visualize the 4th dimension. We have 8 there, but for some reason the 4th dimension thing is not being visualized appropriately. So let me see. What do we have here? New sphere 0.1. 0, 0, 1, 0. This should be the original sphere. And again, it was shown just a second ago. So where has this sphere gone? That's the question. So let's go ahead and remove these guys. Oh, come on. There we are. And now let's do Blender. See, do we have our cube and sphere? No, we don't. Everything's gone. Why? Init cube is equal to define tesseract. Should be okay. Let me just do a print statement after this. Visualize 4th dimension. Scene. Let's go ahead and yank this and put it out here. Paste. I think that might be the issue. Let's go here to blender-p. Okay, good. So we have our single point. That was indeed the issue. So let's go here and let's place the duplicates. And without further ado, we should have nothing. It's all broken. It's all freaking broken. Why is it all broken? Blender. Dang it, we only have one sphere. Where are all the other spheres? We have spheres here, but where did they go? Are they super far out? What are the positions here? Let's go here. Let's see positions. Oh, are they all in the same position? Let me see something. Oh, okay. There they all are. Hey. Okay, this is not what I wanted to see. This is wrong. All right, good. But they are all here, all 16 of them. That's fantastic. Okay, so let's go from there. We have all the positions. Unfortunately, how we visualize 4 dimensions sounds complex. So what we're doing with the 4th dimensional visualizations, we're making an assumption here. And basically the assumption is this. So if you take a 3-dimensional object and you split it up, you cut it along a dimension, you get basically planes, right? We're going to be doing the same thing here. We're going to be splitting along the dimensions. We're going to be setting one of the dimensions equal to 0, and we should be getting cubes in this case, right? Because the idea is, well, kind of trivial in a way. We basically, like, for example, to get slices of 2D data, you set x equal to particular values, and you allow y to vary, right? If you do both are YouTube channels. Oh, I didn't know that. I have not seen Numberphile or Computerphile's 4th dimension visualization stuff, but that would be totally useful, I think, to look at some point. Somehow I didn't see those. Anyway, point is, basically all we're doing here is we are going to show the 4-dimensional object, and then we're going to go through and we're going to rotate the 4-dimensional object. And with the rotations, hopefully, everything turns out okay. And we see basically this guy here. So what we're looking for is something that looks like this. What I didn't know was that Numberphile or Computerphile already did the 4th dimensional stuff. Somehow I've completely missed those videos. So I might take a look at those over breakfast or something like that in a bit. And maybe that should be okay. Oh, I see. I'll take a look at that. That seems interesting. But yeah, so in the end we want something that looks something like this. And I kind of want to figure out how to do it. So that's kind of where we're getting at. Okay, so now we have the question of where these duplicates are. I've been playing around with TypeScript a bit lately. Let me see. So let's go to define tesseract. Oh, I see the problem. Okay. So let's go up to this guy. We see X location, Y location, Z location. So now what I want to do is here, I want to print print. And what I want is cube of count. And I want to print out dot X. Let's go here, remove this guy. Here, and let's do blender-p. Okay, so all these positions are 0, even though we're defining them up here, which means that, which says to me that maybe I'm doing this incorrectly. So let's do this, let's change this instead. So we already have the cube defined. So what I'm going to do instead is I'm going to do this, and now we're going to say cube of count, dot X. Because screw Python. So we're going to do cube of count dot here, and of course the same thing here. Okay, let's go here, and now let's do blender-p. And now we have all the appropriate positions, and we have our little cube being generated right here. Fantastic. Good, so we have our cube. Took a while, but we have our cube. So now let's go over here and let's change this to be 0.01, making it a little bit smaller. Go here to blender-p, and now we have points that seem somewhat reasonable. Scroll down here. Okay, good. So now we have all our points. So now what we need to do is visualize the movement of these points. Basically, the way this will be done is, let me see, we have place duplicates. That's the original positions. We have 2 different sets. How does 4D rendering work within Blender? Again, it's going to be 3D rendering. We're going to be rendering 3D objects, but the 3D objects that we're going to be rendering are going to be projections of a 4D object. The way Blender does it is basically, so again, we're not going to be working directly with 4D objects. Instead, we're just going to be creating textures, and these textures are going to be, how do I put it? These textures are going to be, yeah, so they're going to be, one second, I have to think here. These textures are going to be like what we're working with. So we have like a whole bunch of different objects, and we're going to be moving these objects around. You'll kind of see how it works in a bit. So let's go ahead and let's just define final cube. We're going to do final cube. It's similar to how you project a 3D world on 2D screen. Yeah, it's the same thing. So let's do final here. Cube. It's going to equal to define tesseract. 1 second. 1.5. Okay. So what are we going to do here? Man, I wish I knew that language. So we're going to say for I in init cube, count plus length of init cube. And let's do this. For I in range, let me see. No, I guess init cube is right. Oh wait, can we add two vectors together in Python? Maybe we can. Init cube. 1 second. Let's do total cube is going to be equal to, let me see here, init cube. So you're adding a dimension to the third into 3D instead of creating 4 from scratch. Changing vertices and textures according to viewing position. Yeah, well, I mean, okay. Whatever we do, we're going to have to do a 3D projection, right? Because we cannot see 4D, or unfortunately we can't. Like, I tried to find a whole bunch of different ways in which we could do a visualization of 4D, but I don't think we can. So we're gonna have to stick with 3D, and we're gonna have to do a 3D projection, or a 4D projection onto 3D. But I think this should be okay, right? Because in the end, we should be able to see what we want to see. We'll see what happens, you know? But I think we should still be able to see kind of a good, reasonable estimate of what fourth dimension could look like, and go from there. But yeah, we'll see how this goes. Okay, so I want to append these guys together. Screw it. We have the final cube, we have the starting cube, initial cube here, and we're gonna say I.x. Dagnabbit, let's just do it this way. Final cube here. Tesseract is 1.5. Let's just do I in init cube. Here. Just-in-time compiler? Really? So let's go here and let's do a DD. And let's do yank 3 yank. And let's paste it down here. Okay, that wasn't what I meant to do. Yank 3 yank. And then let's go here and paste that. Now we're going to say final cube. And we do place duplicates of I count original. Good. Now let's go here and let's run blender-p. Okay, and let's see. So this is our first approximation of a tesseract. Okay, let me see. 4D to 3D to 2D. Yeah, this is kind of what we have to do, but that's okay. So Blender does okay with 3D objects. So now all we have to do is go from there. So now I need to define another function, which is going to be basically defining the tesseract, or defining what's known as the connectomy, which is basically drawing lines between objects for the tesseract. So let's go up here and let's look for connectomy. And what do we have here? We should have for I in connectomy, move lines, should be okay. Visualize fourth dimension. 1 second. Okay. And let's keep going. So here it is, connectomy. What do I want? Create connectomy. And we should have draw lines after this. But once we get the connectomy drawn, we can do the drawing of the lines, no problem. So let's go here. And let's pop down here. And let's create the new function. In fact, let's put it just above this one. So let's open, paste, and function to create a list of all possible nearest neighbors. This is not quite what we're doing. So we're going to do function to connect all points on our tesseract. 1 second, with lines. And I think after this function is done, we will call it for today, and we'll come back tomorrow to do the actual movement of this guy. So the idea is then tomorrow we'll kind of do some animations, but today we're just going to get a single image drawn, and we're going to call it from there. So we do connectomy equals 0 for I in range res, for j in range res, for k in range res. That's too bad. Anyway, let me see. So what do I want to do here? We're going to say we have all these individual points. We have pnum, we have pnum plus 1. For what's our resolution? Our resolution is going to be 2, I think. Yeah, so 2 points. So we're going to go through each of these 2 points. And basically what I want to do is connect all of the nearest neighbors. That is totally true. So we're going to do that first. And let's just see what happens if we use the create, 1 second, tesseract. connectomy here. And then we draw lines after this. So let's go here. We have all these guys set. So let's go here and let's do create. 1 second. It's going to be equal to create tesseract connectomy. And we're going to set the resolution to 2. Okay, so now we should have draw lines, I believe. And we need connectomy. So let me go up to draw lines. Make sure I didn't miss anything. Oh, is that not what we have? Lines. Next. Next. Splines, these are all splines. Add lines, that's what it is. Let's go up here and change that to add lines. Go over here and let's run Blender. And let's see what we have. So we do have lines between these objects here. And if we do render mode, let me go over here to rendered. We see, okay, we have a single cube. So now what we have to do is do this with the outside cube. So let's go ahead and keep working on that tesseract connectomy and go from there. So now what we need to do is for I in range here, we do k plus 1. I have to think here. K plus 1 and pnum. So if k plus 1 is less than resolution and pnum plus 1 is less than resolution times resolution times resolution, what are we doing here? I suppose connectomy append count pnum plus 1. So then I also want to append the outside guys. So let's do yank paste, yank paste, paste, and we're going to do count. And I guess we're just going to do count plus. And I suppose what I should do here is I should say total dim is going to be equal to resolution times resolution times resolution. Let's go down here and say total dim. Count. 1 second, I have to think here. We do count plus 1. But in fact, maybe I should do count plus 2 for each of these guys. 1 second, I have to think here. Sorry about this. Count plus 2. Then we're going to do pnum. And then we're going to do plus total dim. And then pnum plus 1. Or, what I can do, where's pnum defined? Equals 0. Wait, where do I define pnum? Pnum is equals pnum plus 1. So, how about we do this? How about we just do pnum is this, and then we also define pnum 2. 2 is going to be equal to pnum. Let's yank this, paste it down here. Let's do pnum plus total dim. And let's go here and change this to pnum out. Okay, so now we're going to do count and pnum out here, and pnum out plus 1. We basically change all of these guys. So pnum out. Up here. There. There. Oh no! I did it wrong. Let's do 4D. Oh, that's not what I wanted. 4X is what I wanted. There we go. 4X here. Okay, now this should do it. Right, let's go over here and let's run Blender-P. See what we have. I screwed it up. I totally screwed it up. Dagnabbit. Visualize fourth dimension. 374. Pnum out was referenced before assignment. Fair enough. So we will do pnum and we'll do pnum out. It's going to be equal to pnum plus total dim. I'm really screwing this one up big time. Yank, paste, remove, RP. Blender. There we go. So now we have almost what we need. Dagnabbit. Let's see, what do we have here? Pnum out. That's the problem here. We have to remove this guy here. So if we do 4x, let's do Blender-P, fourth dimension.py, and let's see what we have. There we have. So we have our 2 cubes, which is a representation of our space that we have here. So now finally we have to connect one last thing. So let's go ahead and yank, paste, yank, paste, yank, paste, and change these to +3. Oh, that's what I meant to do. R3, R3 here, R3 here, And now what we need to do is change these guys to be pnum first and pnum out second. So let's go ahead and 4x here, 4x here, 4x here. Write this, go over here, blender-p, fourth dimension.py, and that wasn't quite what I wanted to happen. Yeah, not quite. We're getting there, but it's not quite there. Dagnabbit. I gotta think. Why are they all connecting up here? That is a super good question. So each of the points... Yep, that's not quite right. Okay, so I have to think again. So what do we have here? If this print's high, fix the uppercase I. The difference is mainly on how I get the I instead of the I. When I'm older, I want to do this. Right now I'm 13, just messing with Unity. That's good. If you're 13 and you're already messing with Unity, that's fantastic, actually. Oh, maybe it's a +1. One second. Let me think. Maybe it's just pnum out. Yeah, maybe this is what I need. Oh, dagnabbit, I screwed that one up. So let's go up here, and let's remove the +1 from this bottom guy. Plus resolution from this guy, and plus resolution times resolution from here. Right here, and now let's do blender-py, fourth dimension, and it's still broken. Dagnabbit. Freaking broken. Oh wait, no it's not. It's all fixed except for that last one. For some reason this guy's not being visualized, but everything else is there. We have our Tesseract ready for animations pretty soon. Let me see, what do we have here? 13 is a good age to be messing around with things, keep at it. Yeah, that's exactly right. So the thing is, you know, I learned how to code when I was super young, and then I totally forgot how to code. So I needed, I don't know, I should have kept at it, but I didn't, and that was my bad. So let's see, pnum out. I gotta think here. Why would that last line not be visualized? So how many lines are we gonna have here? We're gonna have 4 plus 4 plus 4. So that's gonna be 12. Then we're gonna have 4, 4, 4. That should also be 12, right? 1 second, I have to think here. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so then we need, I have to think, 1, 2, 3, 4, 5, 6, 7, 8. Then we need 8. Am I doing this wrong? 1, 2, 3, 4, 5, 6, 7, 8. Wait. Let me just pull this up again. Blender-p, fourth dimension.py. Scroll down. And let's see, what do we have here? So we're gonna need for this initial cube 1, 2, 3, 4 lines. 1, 2, 3, 4 lines from the back, and then 4 lines in the middle. Okay? Just zoom this down. No, but seriously, that happened. I learned programming when I was like 14 or 15 because basically I had this competition with this guy, and you know, so this guy today, this guy is still a friend of mine, but man, he's not the same person he once was. Anyway, this guy and I had this competition to learn game programming, and so I learned C++ so I could learn the game programming, and then after he stopped doing programming, I stopped doing programming, and I should have kept going. I really should have. But I didn't, and so I kind of forgot, and when I entered college, I had to relearn everything. What? Where is this line? How did that line appear? What? Do we have 2 lines everywhere here? Okay, this is... Wait. I gotta figure out what's happening. Holy crap, what am I doing wrong here? I gotta think. I've been used to having just out of range objective, so you can make it exactly right. You know, you have to kind of think about things that are good for you. Now let me think. How many lines are we defining here? We have a total of 8 points, and these 8 points need 12 lines between them. Yeah, right. So let me see. We have a cube back here, 1, 2, 3, 4. A cube back there, 1, 2, 3, 4 lines. Then we have, how many lines do we have total? We have 15? 15? No, we have more than that. Okay, let's see. What's this last one? 35. We have 35. What? Oh, I guess maybe we should need 36? Oh, it starts counting at 0. Okay, that's it. So it starts counting at 0. And then as it starts counting at 0, we have 35. So that's 36. Nope. Oh, Bezier curve. Okay, fair. I'm looking at releasing my first paper, first proper polished mobile game in 2017. Plot twist. Gus is James's friend, and vice versa. Wait, what? I started learning programming for a bet with my friend. Yeah. Yeah, dude, the way I see it, if you guys produce cool stuff, feel free to tell the rest of this community. This community loves cool stuff, you know, and I love that. So feel free to you know, let us know when it's done. Okay, so now I've got to figure this guy out. We have 36 total curves, but how many curves should we have? We should only have 12 plus 12, which is 24 plus 8, so it should be 32 total curves. And let me think, what am I doing wrong here? Okay, so we're connecting these guys together. But I think what I want to do now is I want to actually put these guys in a separate function. So what do we need to connect? Okay, so here's what I want to do. I want to do DD, pnum total resolution. Yeah, so let's remove this guy, and this guy, and this guy. Go down here. Let's do an R2, R2, R2. We do pnum plus 1. Now I want to do 4. And let's do I in range 0, 2. What do I want to do? Let's do 0, 2 total dimension. And we're going to connect these guys. So we're going to say connect to me. Append. And I want to append count. Let's see, what do we have for count so far? Count equals 0. So hopefully we'll still count up. We do count. Then we want to do I. Yeah, it should be I. Then we're going to do I plus total dimension. And that should be that. We do count plus plus. Let's go here. Blender-P. I broke it. Totally broke it. Dagnabbit. What did I do wrong? Count plus equals 1. Freaking wrong spacing. Blender. Scroll down here. And look at that, guys. So we have everything now ready. We have basically a simple tesseract formed. This is fantastic. I'm quite happy with this. Let me go ahead and just put this up over here. And put it up over there. So we have the simple tesseract formed. It's currently 7 o'clock in the morning, which is typically the time I end my stream. Let me take a look at chat real quick. Sure, I'll need to get it to compile tomorrow. Fair enough, everyone breaks things. I really suggest open sourcing some of your stuff. That way people might review it, send you pull requests. A cool way to learn. Yeah, that's true. So, you know, part of the reason I'm doing this stream is so that I can get better at programming, you know? And it's helped. I've definitely become better at doing a whole bunch of different things. This is kind of a way in which I can, how do I put this? Do cool stuff that is not related to work, and I'm quite happy with it. I got version control, and that's sorted. Dude, you are so far ahead of what I was when I was younger. Like, when I was 13, holy crap, I could hardly, like, I couldn't even do, compilation took me a while. I couldn't figure out how to do anything. Control Z? Oh. What? Control Y? I don't know what I just did. I just screwed something up. Let's try it again. But I am quite happy with this. So we have everything we need now for our visualizations. So now all we have to do is actually do the visualization at this point. So we have our tesseract. Good. And we can of course increase the size of these balls to be a little bit bigger. So let's change this to 0.5. Blender. Make them a little bit bigger, and this kind of makes it look a little bit nicer. But that's good for now. So if we do a quick render image here, we should see. Oh, I guess we're a little bit too close. No, we're not. We're almost there. Well, that's okay. And we can, of course, remove that ball in the center there, too. But yeah, I'm happy with this. This is pretty good for a couple hours of work. Happy with that. Let me see. Found some of my first programs. Man, the horror. I just version controlled my C++ projects. Frank, I did not vote for Trump, unfortunately. Sorry about that. Well, not unfortunately. I didn't vote for Trump because he's a freaking idiot. Let's go down here. And let's see. We'll see how the elections go. I will see what happens. Yes, I do live in Japan, but I still have U.S. citizenship. So I sent my vote in about a month ago, or a couple weeks ago, rather, via mail. And no, I did not vote for Trump. So that's okay. So at this point, guys, it is 7 o'clock in the morning. I'm going to go ahead and end my stream here after, let's see, I'm going to first commit this to GitHub. Let me do an ls here. Let's do a git commit. How about git add 4th dimension .py, git commit. And let's do, how about this? I did not vote for Trump. Leave it at that. Git commit 4th dimension, but I'll be honest, neither Hillary nor Trump at this point are compelling candidates. I would be completely honest in that I don't really like either of them. However, one option is clearly better to me than the other, and there isn't really much of an option I have. So it's just something I have to go with. So adding structures for Tesseract visualization. Okay, so now we have everything basically ready. Git push, origin master, and of course, if you need access to this, just feel free to go to my channel right here. The channel is up here. Just scroll down a little bit. Go to my GitHub account, which is right here. Go here, and you'll have the Simulus directory, and we have the very last visualization we did. So feel free to take a look at this if you are interested. It has everything that we need in it. And starting tomorrow, we'll start with the visualizations here. We have a couple animations we need to start with. One with a small cube and growing. And of course, at the very start of tomorrow's episode, at hopefully right at 5 o'clock, we will go ahead and re-explain what we're doing today. So that's about it today. Have a fantastic day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we continue working on the 4D visualizations. And then after that, once we finish the 4D visualizations, we'll figure what we do next. My hope is that we move into genetic algorithms next. That's where I want to go, but we'll see if I can figure out everything before then. So we'll kind of workshop it a bit. But anyway, guys, thanks again for watching, and I will see you next time. Bye, guys. Yeah, I've been having trouble getting up at 5. Sorry about that.